Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will talk about the concurrency in an index structure. That means first we will take an index structures that the tree protocol or the two-phase locking protocol, but an index, then we can use this index as a concurrency mechanism. We will introduce this to protocol scrubbing and the billing tree protocol to have the concurrency in this index structures. Index structures are just structures which follows that for a particular database it uses an indexing scheme. For that, we need to introduce for each search key, there will be an index that is stored inside this index list. And on that index, if we need to find the search key, then we will need to look at the index first, and from that it will point to the actual search keys. Now we have till now discussed about the concurrency in the database management or the actual data or the transactions. But how we can control the concurrency in an index structure? That means while the index has been looked up, inserted, deleted, coalesced and splitted up, how concurrency can be achieved till this? That means can an insertion and a deletion goes hand in hand with each other? We will discuss these two things. Now the index structure that we will use today is an B+3 index. That is the most popular indexing scheme among this database management system. Now the index structure, if we are talking about, now the normal transaction concurrency will be entirely different from this index structure concurrency. Because in the index structure, not only we have to concurrently look for the indexes, but we need to point to the data structure values or the actual set of values. Now what happens when we want to maintain this concurrency, that the leading to an inconsistent state becomes an inheritable problem in this concurrency on index structures. So we need to define some protocols to define our insertion, deletion and lookup for each of these index structures. We will describe two protocols on which some modifications will be there, to which we can go and extend on a concurrency on this B+3 index structure. The first protocol is in crabbing protocol. In the crabbing protocol, we will use the normal insertion, deletion and splitting up on the B+3 that we have described in our previous videos. Now we will describe the crabbing protocol based on this B+3 insertion, deletion and lookup. So when a concurrency in the index structure that we are talking about, it is absolutely acceptable for us if the transaction is made between two indexes until and unless the common indexing is changed between them and the resulting in the same database structures. So the crabbing protocol, first we will talk about the lookups. Now while we are having the lookups on this crabbing protocol, then first we are acquiring a shared mode lock on the root key. Now when we go to the next parent node on this root key, on the child node of this root key, we will acquire a shared lock on this child node of this root key, that is a non-leaf node. Now while acquiring the shared mode on this parent key, we will release the shared mode lock on this root key. Again, we will move like this until and unless we find a leaf node that we are searching for. So the describing algorithm will be first the shared lock for root key, then we will perform first lock shared on this parent key, and release root key. Now in this way it will move until and unless it finds one leaf node and then acquired and shared lock onto the leaf node and then release the parent node. Now the scrubbing protocol uses two-phase locking protocol. As we can see that in the first phase it is acquiring the locks, and the next or the shrinking phase it is releasing the locks. So now the leaf node that we have shared lock on this, now we can reach that node with the lookups. Now what happens with this insertion and deletion? Now for the insertion deletion, in the same way, first we need to acquire a shared lock on this root key. Next, when we are moving to a parent node, if we want to position that node as our insertion or deletion, say suppose that the key we want to delete belongs to that particular index or this key that is happening to be in the parent node, then we need to get first and shared node, and if it is found the search key or the insertion position, then we need to provide an exclusive lock on that node. So first we need to acquire the shared lock, and then we need to check if insertion or deletion, then we need to provide an exclusive lock on that node. So in this way we can either insert or delete in this scrubbing protocol. Now if it needs to split or coalesce or to join two nodes based on the insertion or the deletion, say suppose that the inserting value made the key node as its 2 key on this distribution, now it needs to split the node, or there is too few node for after the deletion, then we need to coalesce the node. Now how can do that? We need to first acquire for the parent node of that node that we need to split as an exclusive lock, then perform the splitting up, then release the lock on both the node and the siblings. Now how can do that? We need to exclusively lock its parent. First we need to locate it, then make the exclusive lock parent, and then we need to split or coalesce, and finally we need to release the parent and its siblings. Now we can see that the scrap protocol, why it is naming so, because it first acquired the parent lock, then it's code by the left right, just like a crab walks within click that it is moving in that way. That is the name is scrubbing protocol. But what happens that how can it achieve this concurrency in this index structure? See, in this splitting or coalescing or inserting or deleting, we are acquiring a shared lock, and after that we can provide an exclusive lock if and only if that value we need to access, either it is a search, insert, split up or delete. Now what happens that other transaction can easily get the shared lock on the same root node or the same parent node for having their own access. Now if it is only for the delete and insertion, then we need to stop and wait for the other transactions while the transaction is performing the insertion or splitting. Now in this way it provides the concurrency in this index structure on a B plus tree, which provides the splitting, coalescing, redistributing, insertion, deletion and lookup for the concurrency in structure. Now this scrubbing protocol has one advantage, that it is very simple to achieve, because first the shared mode locks are there and after that we are acquiring an exclusive lock. But one disadvantage lies with it, that with the concurrency we are achieving in a situation that we are having a particular scenario where we can have the extra overhead of having a shared lock from the root to the leaf node if we want to insert or delete the value. That means for every node it first acquired the lock, then release the lock. So the locking overhead is there for this scrubbing protocol. Now there is one more protocol that is known as a B plus tree link protocol. So this B plus link protocol suggested some modification to the scrubbing protocol so that it can achieve a better concurrency with less overhead of locking. So in the B plus link tree protocol, for going to, we first need to know what is an B plus T link. So the B plus link tree suggests that every node will have a pointer to its right sibling. That means if it is a parent node, if it is a leaf node, it will have a pointer to its right sibling if it is belonging to the same level of this B plus link tree. So that will not only help us make the insertion deletion help, but also it will help us to give a better concurrency, because at the same level now it can provide an exclusive lock on this leaf node of having the particular key, not having all the locks on this parent. Say suppose a parent has 3 or 4 key nodes or the leaf nodes. Now only one is desirable for our insertion or deletion. So what we need to perform? We need to provide an exclusive lock on the parent. But in this B plus link tree, we are making the link tree in such a way that it contains the pointer to its right sibling, so that performance of the lookups insertion becomes extremely easier here. So first let us define this B plus tree link. Say suppose we are creating an index on the department on this instructor relation, and the instructor relation will get this department index on an B plus link 3 plus 3. That means n equals to 3 here. Now you can see that history as the root node, so we can have the lesser values of history in the left one while having the greater values in the right one. Now engineering is lesser than history, so it goes in the left side, and in the right side we will have the greater values. So as with the B plus link tree, we know that for except the root node, for every node it will have an pointer to its right sibling. So now the engineering will have a pointer to the key that is containing music. So now we are having the engineering's right side as the engineering and finance, because for B plus tree we know that every node belongs to the leaf node as the final search key values. So now this is my B plus link tree that we have made with every pointer to its right sibling. Now we will just describe this tree protocol according to which we can perform the lookup, insertion, deletion, splitting and coalescence. Now in this B plus link tree protocol, first let us look up performance on this. So the first one is lookup. Now for every lookup that it is performing, it needs a shared mode lock on that particular search key before reading the value. Say for an instance, if I want to read this engineering, then we need to look on this engineering key field on this non-leaf node. Now this engineering must be shared lock on this leaf node first, and then we can search on this value. Now compare it with this crabbing protocol, where from the root node till the leaf node we need to acquire the shared lock, release the lock, shared lock, release the lock until and unless we are reaching the leaf node. So now in this engineering we are only having the shared lock on the key node. So now the shared lock on key. Here why I am mentioning key, that the key can be either the leaf node or in this parent node, but as it's the B plus tree, we should come to the leaf node at most to search key valuation. So now if there is a deletion and insertion and this lookups performing hand in hand, that means simultaneously, then what can happen? Say suppose that the resultant data is splitting up into the new one. say that the B plus link tree is performed within concurrent execution. So it can happen that one transaction is performing the lookup, another one performing a deletion or insertion. So when the deletion or insertion is performing hand in hand with this lookup, then we must provide the exclusive lock on that particular key. Now if it is lookup for insertion, then exclusive lock must be made to this key where we want to insert or delete, and then we must go for this right sibling pointer. So that is the use of this right sibling pointer. Now if it is inserting a value or deleting the value, then we must look for the right sibling pointer that will contain the value of this lookup. So now it will be happen that shared lock on this right sibling. Now we can perform the lookup in hand with this insertion or deletion. Now the second one is an insertion. Now for insertion and deletion both, it just get the shared lock on that first key node and then transfers or updates this shared lock to the exclusive lock if it finds that stage node. So first it needs to perform the lookup on that node. Say we need to insert a value that is history and we go into this key field. So first we need to go for the lookup on this search key. That means shared lock on that key. Now if we can notice that the position where we can insert the data, it will upgrade our lock to an exclusive. So the upgradation means from shared to exclusive it will be there. Now it will perform the insertion and it will be following with the two-phase locking protocol, because for one case it will be shared lock on key then upgrade, and after the insertion is there it will be release the lock. It is unlike the crabbing protocol which do not mention the two-phase locking protocol, because while hand in hand it release the lock, then gain the lock on this next node, release the lock, gain the lock on this leaf node. So now this B plus tree link protocol can give us that it is following the two-phase locking protocol. Now this is for the insertion or deletion. Let us talk about the splitting. Now to split the value, that means we need one node for which the original node it was. So first we need to get an exclusive mode lock on this original node. Now that we can split it up into this right sibling, so the right sibling now become my original node and the original node become the left child of this right sibling. So now we need to acquire the exclusive lock on the right sibling and then release the lock on this particular value. Now after the right key is exclusively locked, it will be made as a new original node, and the original node, as we have said, will be my left child node, and the original node is in the left child node and the part of the left child node will be my right child node. So now we need to acquire one shared lock for the left child node. Then we need to perform that all the key that we have split it up, that now my original node is left node a part of become the right sibling with the pointer to the right sibling, and now again my right sibling become the original node. So now we can release all the locks. The last one is in coalescence. That means if there are too few queues after deleting a key from a field, then we can say that we need to join those fields to have one merged value so that we can have a minimum number of value in this particular field. Now to coalesce, just like the split, first we need to exclusively lock the key that need to be coalesced with its parent node. First, that the coalesce node need to be exclusively locked, and also the parent node which will be joined with this coalesce node need to get an exclusive lock. So now we are not getting the right sibling but the coalesce node and the parent node. And after that the parent has got the exclusive mode lock, then it will be joined with the coalesce node. Next the coalesce node will be freed. After that the parent will be freed. See here, we cannot reverse the order of releasing the locks for parent and coalesced, because until and unless the parent lock is released, the coalesced lock cannot be released. So first we need to release the lock for the coalesced node and then for the parent node to provide the concurrency, because now we are dealing with the concurrency. If we have released the parent lock first, then the coalesce node lock can be get by another node on that particular parent, which say we are inserting and value. But insertion and coalescence cannot go hand in hand, because they will provide an inconsistent state while maintaining the concurrency. So we must release the key first, then the parent. So if we have observed this correctly, that for the insertion and deletion, one may have locked in that item, unlock in and relock it again for the deletion. But for the lookup and the split and coalescence, we need to search through the entire tree, go to the exact node, then go for the exclusive mode lock on that particular key node. So that is the main advantage of an B plus link tree, which can get the profit of having the pointer to the right sibling in both of these lookups, the splitting, but not the coalescence. So now we are having this B plus link tree, and we will now just insert onto our B plus link tree that we have used and then perform a lookup to it. Now let us first insert chemistry in our original B plus link tree that we have described. If we want to add chemistry, if we can recall, then we had history as a root node, on which we have the left root node as an engineering, and onto the leaf node we had biology and computer science. Now if I want to add chemistry here, then we need to go for the left of history to engineering, perform the lookup just as in the case that we have described in the protocol. Then we found that biology and computer science is there where we want to insert. So we need to split up. So how can we split it up? We are performing the protocol. First we are acquiring an exclusive mode lock on this biology and computer science. Then we are having the right key to this pointer.
Sure.
Then we are having the right key to this pointer, where we can find there are almost one key and there are almost two keys that are on the right keys. So we have to split it again. That means we need to add a new node on which the resulted value will be added. That means now chemistry will be added to the resulted value, but as chemistry is lesser than this computer science, that is CO, which is greater than CH, so we will coalesce bio and chemistry with the exclusive mode key on this parent and this leaf, and then release the lock on this leaf node. Finally, we will release the lock on this parent node. Now let us perform and insert chemistry in our original table. Now with the engineering, the computer science will be a key, otherwise we cannot have the right sibling pointing to the computer science. So now it will be splitted up into biology, chemistry and computer science, so that the computer science can be coalesced with engineering, so that we can have an index to these values. Now on this computer science on the left hand, we had this biology and computer science. Now as chemistry is inserted, we are producing an exclusive mode lock on that one and make biology chemistry there, and a computer science will at the right side of this computer science. As we can see, the original node biology computer science has become biology chemistry, and the computer science will be the right sibling of this computer science index. So now this becomes my new B plus link tree with the insertion of chemistry here. Now let us perform the lookup on computer science. Say it will go for the history one, then the computer science. So we are not providing any lock till now. And after the computer science, it will go for this node. Now it need to shared lock on this particular key because it know that it has reached the index for computer science. So the right pointer will always point to the actual index value, the search key. So now it will put on shared look and then look up on this computer science field. See, the insertion and this lookups doesn't handle on this deadlocks because we will provide on that key for the shared lock. Now for the case of coalescing, in case of the deleting, we can lead in inconsistent state because sometime deleting a value will lead us in a coalescent set that cannot point to the right sibling. So in that state, we have an inconsistency while maintaining this concurrency. Now this B plus tree link protocol also have a higher level of concurrency if we give key level locking other than this index level locking. Now in this key level locking, we can actually lock the particular key that we are having, not just the link on that key. That means the right sibling concept will not be there, only we need to lock the value on that particular key. Now another increased concurrency can be given in this index structure while we are having next key locking protocol. In this next key locking protocol, not only the key which is being accessed like the insertion, deletion or splitting up, also the next key, that means the right sibling of that key will be also locked. Now the consistency can be maintained in this next key protocol that the key which is the next one to be accessed. That means if we want to insert that a particular value here, like this one, computer science goes on this right field. So if we have not locked this right siblings or the next key, then we may lead in an inconsistent state because some data may want to insert value in this key and someone is inserting in this field. And splitting up requires the next key also be exclusively locked. For the insertion, lookups and deletion, all three of the cases, the next key locks not only the key but also the next sibling of that particular node. So in this way, we can provide concurrency in index structure by the scrubbing protocol, B plus link tree protocol, key and next key locking protocol. Among this, we can see that only this B plus link tree protocol follows the two-phase locking while others are not following the two-phase on this locking protocol. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.